another one, so hopefully you do. Okay. All right. So we're just going to get this one started. We'll spend about 10 minutes on this, and then we'll finish up with the quiz. All right. I can actually just erase that top line. I don't know why that's there, because I rewrote that right here, so that's kind of a typo. Anyway, it doesn't matter. A rational expression. Does anyone know what the word rational means in math terms? It kind of says it right here, but so it doesn't mean like clear thinking or like it's not like rational thought. It means fraction. So rational in the math world means fraction. And so a rational expression is a fractional expression specifically where both the numerator and the denominator are polynomials. And so each one of these examples here, I've got 3 examples. They're all rational expressions because everything in the numerator and the denominator are polynomials. Right? The 2x is a polynomial, x minus 1 is, x squared plus 1. All these things are polynomials. What makes them polynomials? Because in a second I want to write down something that's a non-example. So right next to here I'm going to put non-example down. And so what makes something a polynomial so we can write down a non-example? That was something from the last page. What are the kind of the key features of a polynomial?
The exponents have to be possible integers?
Yeah, we need exponents that are positive and integers, which means they're whole numbers, right? And so if you look at all those, they all have positive or at least non-negative exponents that are integers. And that's really the only thing that we really need. And so any sort of fraction that doesn't have either a whole-powered positive exponent is a non-example. So for example, square root of x doesn't work, divided by e to the x. Neither of those things are polynomials. And so we can't say that those are rational expressions. A rational expression is it's more of a vocab thing. It just means that everything in the numerator and the denominator is a polynomial. Okay. Questions about that at all? So domain. I'm going to put a star next to this because this is very important. It's something that we're going to talk about all semester long, and it's something that I feel like people sort of fall behind on, and then it haunts them the rest of the semester. So let's make sure we understand this, and if you have any questions as we go through this, please let me know. The domain of an algebraic expression are all the numbers that you're allowed to plug into that expression that doesn't result in something bad, so that results in a sound expression. So it's everything you're allowed to plug in. Now, there's infinitely many numbers that usually fit in a domain. And so rather than thinking about every single number that you can plug in, it's usually more helpful to think about the numbers you can't plug in. And then you avoid those numbers when you write the domain down. So that's what I wrote here. To find out what the domain of an expression is, you want to consider all the numbers that when you plug it into the expression, you get an undefined value. And so this is basically saying you think what numbers are problems to plug in. That's the way you approach these problems. And again, we're going to be thinking about domain of lots and lots of functions this semester. And so this is a really good time to start understanding this. In my previous notes, I had written down that we use set builder notation, but I've since started using interval notation. So will you change that to interval notation? Forgot to change my notes around. So we end up writing down our answer in interval notation. And we've already practiced using that, which is one of the reasons why I like to start to switch over there. Does everyone see that? I just changed that word. I used to say set builder notation, and I changed it to interval notation. Okay. So when you're thinking about, so we're going to find the domain of all these things right here. And when you're thinking about what you can't plug in, there's only ever 3 problems, or 2 problems. Sorry. The possible problems are you might divide by 0, and we don't want to do that. And you might take the square root of a negative number, or an even root of a negative number, I mean. Not necessarily square, but you can't take any even roots of negative numbers, or both of those things. And so we just look at the function and we think, when is that going to happen? And then we avoid those numbers. For example, in this first equation, are there any times, are we ever going to take the root of a negative in there? Are there any roots in that equation, I guess is my question. No, there's no radicals in there. And so we don't have to worry about taking the square root or the 4th root of a negative number because there aren't any roots. So that's fine. So we don't have to worry about b in this first one. But we might divide by 0. Right? What is going to make it so that when we plug it in here, when we plug an x in here, what x is going to make us divide by 0? 2 or negative 2. Good. And so if the negative 2 isn't jumping out to you, the first lesson here is you should factor the denominator if you can. So, whoops, I just wrote down. I just said factor it and then I didn't do it. So we just talked about factoring, right? So we can factor that into x minus 2, x plus 2. And we see that the function is undefined if we plug in either of those numbers. Because we'll divide by 0, right? So because we will divide by 0. And so that's indicating to us that 2 and negative 2 are not in the domain. Those are the only 2 numbers we're not allowed to plug into this particular function. Any other number you can think of is okay. 0 is fine, a million's fine, 2.8 is fine, pi is fine, right? Any number except 2 or negative 2. Does that make sense? And so then when we write down the domain, we do so using interval notation. And we've already practiced doing that, so I'd like you to give it another try. And I'll just remind you real quick how we do that. This was from the homework, the very first homework, the orientation, right? So if we want to write down all numbers except, say, 5, do you remember this was in the orientation set we talked about? That would be minus infinity to 5, union 5 to infinity. Because we're skipping over 5 by putting parentheses around it, right? So this is like every number less than 5, and this is every number greater than 5, and 5 itself is not in either of those 2 sets. And so this would be every number except 5. All right, so take a second and think about what every number except for 2 and negative 2 would be. So you want to do that same thing where you put parentheses around 2 and negative 2, except you're going to have 3 intervals instead of 2. You're going to go minus infinity to negative 2, negative 2 to 2, 2 to infinity. All right, just take 1 second and practice doing that, because we're gonna write down lots of intervals. The more practice you have with that, I think the better. And then once you do that, I think we'll probably stop here. So I know I gave you no time at all, but hopefully you at least thought about it a little bit. I want to make sure you have enough time for the quiz today. The domain of this particular function will be the following. It will be minus infinity to negative 2. We're going to skip over negative 2. We're going to go from negative 2 to 2. And then we're going to go from 2 to infinity. And that would be the domain of this function. And you can see that we're skipping over negative 2, and we're skipping over positive 2. Yeah?
Okay, so last time, like in the orientation, we did like negative infinity, -2, and then union 2, and positive infinity. So can you do that too, or you have to write it with 3?
In the orientation set, you were only skipping over one number, though. And in this one, we're skipping over 2 numbers. And so we needed an additional interval to skip over an additional number. If we wanted to skip over another one, we would need another interval to skip over that one, too. Yeah?
I'm probably gonna double check, but I was having an issue with the brackets.
Yeah, thanks for bringing that up. So again, in the orientation set, it wanted you to include one of the numbers. It said, like, from -5 to 0, but skip over -2 and 0 or something. But he wanted you to include -5, for example.
Oh, okay, that's, because I was wondering, I thought it was excluding that, and, okay, I thought there was an issue with the brackets.
Yeah.
Okay.
And so there's no brackets in this one because we're skipping over the 2's, and so that's why there's parentheses there. And then we put parentheses around infinity because we never actually get to infinity. Infinity is not a number, so it's just implying that it keeps going forever. And so that's why there's no brackets in here. We'll see in the next one. The next one will have a bracket, I believe, if I'm not mistaken, but we'll see that next time. Other questions? All right, I'd like to stop here and do the quiz. All right. So last time we were talking about rational expressions. This is where we ended off. And I'll just remind you quick that a rational expression is when we have a fraction. It's a fractional expression where the top and the bottom are both polynomials, right? And so we had some examples of what those look like right there. One sec here. We had a couple examples of what those look like right there and what they maybe don't look like right there. And we had talked about how we find the domain of these algebraic expressions. And so the last thing we mentioned was when we're talking about domain, and this is something that's going to carry through the entire semester. When we talk about domain, I actually just posted the domain homework last night too, or this morning. When we're talking about domain, these are the 2 things we need to think about. Are we ever going to divide by 0? Are we ever going to take the square root of a negative number? So we think about when that might happen, when those 2 things might happen, and then we avoid those numbers. Those numbers are not in the domain. So in this first example that we did, we factored the bottom, the denominator, into x plus 2, x minus 2, and this showed us that you can't plug a 2 in or you can't plug a minus 2 in because we'll end up dividing by 0. And so when we wrote down the domain, we skipped over those 2 numbers, right? That's what this was down here. This was us skipping over 2 and minus 2 in the domain, right? And so let's look at this one. Let's actually skip to the last one first because it's an easy one, and then I want to just get it out of the way and make sure there's enough room for this one. So I put this one up here to show you maybe what? I mean, is there any problem here? Are we ever going to divide by 0 in this equation, or are we ever going to take the square root of a negative? Right, so dividing by 0 would mean we'd have to have a fraction with a variable in the bottom, and taking the root of a negative means we have to have a radical. And are either of those things in here? I know it's early, but I can wait. I can wait for an audible answer. No, right? There's no fractions. Thank you very much for that. There are no fractions. There are no radicals, and so there's no problems with this one. So just keep in mind that sometimes you can plug anything in. And so on this one, what we want to write down, and I would just try to use as little room as possible because this is kind of a longer problem. There's no possible problems on this one. Right, we can plug anything into that equation. And so the domain in this case is everything. And so we would just put minus infinity all the way to infinity. And so just be aware that there's functions out there that have that domain. And in fact, many functions have that domain. Any function that doesn't have a fraction or a radical in general will have a domain of minus infinity to infinity. And the reason I wanted to put this down, not just to show you that some have domain minus infinity to infinity, but to also write down that the reason it has that domain is because it's a polynomial. And so a fact about polynomials is that they have the domain of all real numbers. So polynomials have a domain of all real numbers. So you can plug any number into a polynomial. So that fits very nicely into what we did in the last section, which was talking about polynomials. So any polynomial, you can plug any number into it. Any questions about domain before we go on, before we do this last one? You know, I recognize that this can be a tricky thing sometimes if you're not familiar with it. And so I'm happy to clarify anything if you have a question at this point. Because the last one's a little more involved, right? So I want to talk about the domain of this thing, and this one has a radical in the numerator, and it's a fraction, so we might divide by 0. So we have to worry about both these things. We have to worry about dividing by 0 and taking the square root of a negative in this one. Okay, so let's focus on the numerator first. So the numerator, the square root of r, we don't want to take the square root of a negative. And so I'll just say we can't take the square root of a negative. So in the square root of r, we need r to not be negative. So r greater than or equal to 0 means not negative, right? So that's telling us something about the domain. So already we know we can't plug in -1, for example. Is that okay? Okay. And then from the denominator, if we look at the denominator here, we know that we can't divide by 0. And so we need r plus 9 to not be 0, and we need r minus 12 to not be 0. Because then either one of those things happen, we'll divide by 0. And so when is r plus 9 going to be 0? -9, right? We can solve this equation for r, and this would mean that we can't plug in -9. And from the other one, it means that we can't plug in 12. Good. Right, because if we plug in a 12, it'll make the r minus 12 0, and then we'll divide by 0. If it makes the -9, sorry, if we plug in -9, it'll make the r plus 9 0, and we'll divide by 0. And so we don't want to do either one of those things. And just to be clear, if we make, just in case someone's wondering this, if we make r plus 9 0, but r minus 12 is not 0, they multiply together. And so we only need one of them to be 0, because it'll multiply and make the other one 0. So either one of those, both of those things need to be avoided. Are there questions about this so far? Because we've written down all the numbers we want to avoid. We want to avoid negative numbers and -9, so that's already avoided, but 12 as well. So negative numbers and 12. Can't plug it in. And so we want to write that down. Are there questions about that? Let me write it down and then let me know what you think. So I'm going to avoid those numbers. And so let me ask you this. Can we plug in 0? I know we cannot plug in a negative number, but is 0 okay? 0 is okay. The square root of 0 is 0. And so 0 is okay. So I'm going to include it with a bracket. But then we want to skip over 12. And so I'll go to 12 and skip it like that. Remember that little thing where we write parentheses around both sides of that 12, and that's skipping over it. And then we can go all the way up to infinity past 12. And so that's the domain of that particular function. 0 to 12, including 0. We can include 0, but then we're going to skip over 12 and go all the way to infinity. And we'll see this again in a few pages down the road. We'll revisit domain on some other functions in, let's see here, 5 or 6 pages maybe a little bit longer than that. But it's coming up in the near future. We'll revisit this stuff. And, you know, I've said this before, but we'll revisit it all semester. We're all about domain. We always want to know what we can and can't plug in. Questions about that? Okay. Oh, there's a little bit more on this page here. Great. So this is kind of our fraction section, and so we've started talking about what we can and can't plug into fractions, and now we want to talk about how to deal with them. You know, how do we add them together? How do we multiply them? How do we get rid of them? Right? If we have a fractional expression and we don't want fractions anymore, how do we get rid of them? And so that's what we're moving into right here. Is we want to figure out how to handle these things. So the first thing we're going to talk about is multiplying them together. Having a real hard time with this projector this morning. Sorry, let me see if I can get this going. All right. So this first box here is reminding us how we multiply fractions, and this is something we already talked about the other day when we were talking about fractions. Just, you know, we were briefly talking about fractions. But this is telling us when we multiply two fractions together. Oh, I'm sorry. This is multiplying is on the next page. This is simplifying them first. This is saying when we have things that are already being multiplied together, we can cancel out things from the numerator and the denominator, right? So if we have a times c divided by b times c, we can cancel out the c's and be left with a and b, right? So like for example, let me just clarify this though. Don't make this mistake. If we have plus in between the two of them, we are not allowed to cancel. So this is not equal to a over b. So be careful about that. That's another common mistake. If they're being multiplied, yes, we can cancel. If they're being added, if there's addition between the two of them, you cannot cancel them. All right, be careful about that. And so the way we usually see these problems are we have like some factors, and the factors end up canceling. So like on this first one, let's take a second and think about how we could factor the denominator here. So the numerator can't be factored. But the denominator, what are factors of negative 16 that add up to negative 6? And the way these problems usually work, while you're thinking about that for a second, is we want something to cancel, and so the numerator is going to be one of those factors, right? X plus 2 is going to be one of the factors because we know we're going to cancel it out. Like that's just, unless this is a trick problem or something, we're going to cancel something. All right, so x plus 2 is going to be one of them. What's the other one? Good, x minus 8. Because minus 8 and 2 multiply together to give us negative 16, and they add together to give us minus 6. But now this is a situation where we have multiplication on the bottom. Right? We've got x plus 2, and it's multiplying times x minus 8. And so we can cancel out the x plus 2's. Right? And we get 1 over x minus 8. And again, it's because those things in the bottom are being multiplied. That's the important part there. Oops. Any questions about that one? All right, so in the first one, the numerator couldn't be factored, but in the second one, we can factor both those things, right? Yeah, so take a second and factor those things. So this should factor into two things. It'll be, you know, one factor times another factor on the top, and one factor times another factor on the bottom. And two of them will be the same, and we'll be able to cancel them, right? But take a second, this is good practice for the homework and everything. Take a moment and just factor that top and that bottom. And again, you should have a matching factor on in each piece. What's the numerator factor into? So factors of -3 have got to be 3 and 1, and one of them's got to be negative, right? So if you're just kind of going through the thought process, then there's going to be a 3 and there's going to be a 1. And there's going to be an x, obviously, and we just wanted to decide whether we put a plus or a minus between them. And I want them to add together to give us -2, and so I want the 3 to be negative because that's more negative, and then we'll add 1 to it, and then it'll give us -2, right? And then when I'm looking at that, I already know the bottom, before I even do anything, I'm very confident that one of these factors is going to be either x minus, or x plus 1 or x minus 3. Because something's going to cancel. Because that's this type of problem, right? And so that gives me a little bit of a hint, at least. And so we've got 5 and 1 as a factor, so there we go. This has got to be an x plus 1 then, because we know it's going to factor, or going to cancel. And so that means the other one, it's a 5 here, right? And we want 5 to add to 1 to give us that 6, and so we do a plus in between there. And again, now we have the situation where we have things being multiplied on the top, things being multiplied on the bottom, and so we can cancel the x plus 1s because they're being multiplied. And we'll just end up with x minus 3 over x plus 5. Any questions about that one? Okay, so let's just remind you about canceling things on the top and bottom. Let's talk about multiplying and adding and dividing fractions now, because that's the stuff we really want to deal with. And we'll do a little review of regular fractions too, not just rational expressions, like regular fractions, I mean. Alright, so when we're multiplying fractions, this is the multiplication page. When we have two fractions that are being multiplied, like it says in the first box, you multiply just straight across the fraction. Multiplying fractions is super easy, right? It's easier than adding them, which is counterintuitive, right? Usually you learn adding and then you move on to multiplication. Here we want to start with multiplication and then we'll move on to adding, because adding actually is more difficult. And that's what this box says. When we have two fractions that are being multiplied, you just multiply the tops together to get a times c, and you just multiply the bottom together to get b times d. So for example, let's say we had 2/3 times 4/5. We just multiply the two numerators together to get 2 times 4, and then we just multiply the two denominators together to get 3 times 5, right? And we get 8 over 15. And it works the exact same way when you have polynomials in there too. Like, yeah, there's a little more work, but we're still doing the same kind of thing. So like on this first one, we've got two fractions that are being multiplied, and we're just going to multiply the numerators together. We multiply those together, and we multiply the bottom together as well. Right? We just kind of put them right into the same fraction. They're no longer, I mean, it looks like the same problem, but now they're in one fraction. And now we're building on the last section because now we want to simplify that, right? So we want to like FOIL out the numerator. We can FOIL out those two. And then we want to send the p and the denominator through that trinomial, right? So we'll do some distribution here. So we'll distribute the numerator and the denominator, doing our FOILing kind of thing. And we get the following. We'll get 4p minus 24 plus p cubed minus 6p squared. And yeah. And then on the bottom we get p cubed plus 2p squared minus p. And that's all we got. Well, let me ask this. Can we do anything else? Like can we, I guess what I'm getting at is, can we cancel anything? Like I've got a 2p squared on the bottom, and there's a 6p squared on the top. So those are both p squareds. This is a p cubed on the bottom and a p cubed on the top. Can I cancel those p cubes? I can't, and why is that? Tell me. Yeah, thank you, Jackson, because they're being added, right? So this is, I'm just trying to point out this property here. Because there's addition going on between the terms, you cannot cancel things. And so that's why we cannot cancel any of those terms, even though they're like terms on the top and bottom. Right? If they were being multiplied, if all that stuff was being multiplied together, yeah, we could start canceling, but they're not. Okay. Questions about that at all? Okay, great. So dividing is very similar. So I just did one example of multiplying because dividing uses multiplication. And that's what I'm trying to say in these boxes here. So when you're dividing one rational expression by another, you use the following property combined with the above multiplication property. So when you have a divided by a over b divided by c over d, what we do is we take the second fraction and we flip it upside down. We invert it. Right? It became d over c, and then we multiply. And then when we multiply, we use the above property that we just talked about up there. We multiply straight across the numerator and the denominator. Right? And so division is a form of multiplication. For example, let's do a quick example with numbers, with regular fractions here. So 2/3 divided by 3/5, let's say. What we do is we leave the 2/3 alone, and we flip over the 3/5 and multiply. So it would be times 5/3. And then we just multiply straight across the top. We do the 2 and the 5 together, and the 3 and the 3, and we get 10 over 9. Okay, and it's the same thing with these more complicated fractions. We'll just have to do some distribution and things like that. Any questions about that property? All right, let me do one, and maybe ask you to try the other one. Let's see which one of these is better to do. I'm going to do the one on the right here. So we've got z plus 10 over 1 minus z squared, and we're dividing it by 10 plus z divided by z. And so we want to leave the first fraction alone, don't touch it, and then we flip over the other one. So 10 plus z over z becomes z over 10 plus z. We just flip that one over. And we're multiplying. We're now multiplying straight across. And so we can go ahead and FOIL. But before I FOIL, I'm just wondering if anyone sees something else we might do. That might sound good. What were you going to say, Anna? Yeah, good. So what these guys are pointing out is that we've got a z plus 10 and a 10 plus z. And those two things are the same, right? Z plus 10 is the same thing as 10 plus z. And so we've got kind of this situation where we have a times b over c times a, right? We've got a's are the same even though they're across from each other. And we can cross out those a's and just get b over c. And so we can cross out these z plus 10s and not have to worry about any distribution. So that's one thing we could do. And that's generally the better thing, right? Because this is nice and simplified now. We can't do anything else to it. It's very nice. If you multiplied it out, though, and you might want to try this as a good practice, like maybe you're just not confident about this and you want to try one. If you multiplied it out, you would get this. And so this is something you might want to try and just double check to make sure you can do it. And again, what I mean by multiplied out is I mean you got to FOIL the denominator, you FOIL that out, and you would get that. And then if you multiply the z through z plus 10, you get z squared plus 10z. So that's just something that you might want to try because you've got the answer and you can try it one more time. I'd like to let you try this other one. Have any questions though at this point? Does everyone feel okay about this? So try this other one then. So see what you get with that. It's a little more complicated. We've got some cubes and squares in there. You're going to have to FOIL. There's nothing you're going to be able to just like cancel right out. It's not going to be that easy. So give that a try, and then check it with your neighbor if you would, please. I'm just going to get it set up and let you take it away. All right, go ahead. Is Chris here? Is Chris coming? Sorry, different Chris. You okay? Give anyone a hand right now? You could do that if that was true, but notice that doesn't factor into that. Why do you use those
But so if that were a minus, you could. Oh, this is.
Yes.
Okay. So it's awfully quiet. I know some folks are still working, but if you are finished, please do really give it a check with someone next to you. And if you're too tired to work this morning, I'm not going to sort of force you to, but it's good for you. You should really try it. The sooner you start practicing this stuff, the better. Alright, I'm going to start working on this one. So when I start doing this, I'm realizing that we've got a couple fractions being divided, and so I took the one on the right and I inverted it and I'm multiplying it now. So you change it into a multiplication problem, right? And then when you do that, you just have to FOIL out the top and the bottom. And so when I FOILed out the numerator, I get x squared plus 6x minus 2x minus 12. And when I FOIL out the denominator, I'll get x to the 5th plus 4x cubed plus x squared plus 4. And then when I'm looking at that, I'm trying to simplify it, right? And the only thing I see the simplified is we've got a plus 6x and a minus 2x. And so we can combine those, and we'll get x squared plus 4x minus 12 over the same denominator, right? There's nothing to combine in the denominator, so we just leave it. And that's a nice answer. You guys get that one? Are there any questions about it? Okay, great. So, not going to do another? No. But I did want to point out just one thing, and that is sort of the takeaway from this page. These are just like fractions. They are fractions, right? And so you treat them like fractions, and you use the fraction properties. If you're going to add them, you use the fraction. Same idea of adding fractions as adding rational expressions. Rational expressions are fractions, and all fraction properties apply to them. And so whenever we see a rational expression, if we know how to deal with a fraction, we just do the same thing. Or vice versa, if you get good at dealing with rational expressions and then you see a normal fraction, you should know how to treat the normal fraction because it's just like rational expressions, right? So they're the same thing, and we're practicing both in some sense right now. All right, let's keep going. Are there any questions? I'm happy to stop, pause, and answer some questions if you have them. Is everyone all set with this page? No one's writing? Okay, great. So now the slightly more difficult topic, which is how do we add them? How do we add and subtract fractions? And how do we apply that to rational expressions? So let's read through these instructions real quick. So in order to add or subtract two rational expressions, just like any fraction, you have to have the same denominator, right? We need a common denominator. And so the way we figure out what the common denominator is, we need a common denominator, is you have to determine a common multiple of both the denominators, all right? So the easiest way to do that, the easiest way to find a common multiple, is to factor the denominators, and then whatever the product of the distinct factors are, so distinct is important, is going to be the common multiple. So that is, multiply together each non-repeated factor of each denominator. Right? And we'll look what I mean by that. But we're going to be looking at the factors of the denominator, which means we need to factor it, right? Once you have the common multiple, you just make sure both pieces have that by multiplying by the common form of 1 to reach that denominator. I know this is like a bunch of not helpful instructions, but I think once we do a couple and you go back and read these later, it'll be helpful. And then once both expressions have the same denominator, you add or subtract the numerators while keeping the denominator the same. I can't stress that enough. I know people get confused by that. So for example, if we have something like this, 4/3 minus 1/3, you leave the denominator, a third, and you subtract the numerator. I just want to be clear about that. And we'll do the same thing with these. Right? So notice that the denominator didn't change. What changes is the numerator. Can I clarify anything with respect to that right now? All right, let's look at an example, and you can let me know if you have a question after that. So when I look at this first one, what I mean by looking for the distinct factors of each denominator is I look on the left here and I see that this one has an x minus 3 and this one has an x plus 7. And so putting the two of those together, they're each distinct, first of all, right? They're their own thing. And so I put the two together and that gives me the common denominator. So the common denominator in this one is both of them together. X minus 3 times x plus 7. Because the x minus 3 came from the left one, and we got the x plus 7 from the right one. And so we just combine the two of them, and that'll be the common denominator, right? Any questions about that? Okay, so now we just want to make sure they both have that denominator, and then once they do, we can combine them. And so the one on the left already has the x minus 3. So we don't have to worry about giving it an x minus 3. We want to make sure it has an x plus 7. And so I'm going to multiply x plus 7 into the denominator. But in order to do that, I need to make sure I'm multiplying by 1. And so I multiply by x plus 7 divided by x plus 7. Because this expression on the right equals 1. And so we're not changing the problem by doing that. All right, and we do the same thing on the right, except we do it with the x minus 3. So we do x minus 3 over x minus 3. Again, it's really important that you multiply by a form of 1, because this is x plus 7 divided by x plus 7 equals 1. And so this is not changing anything. You're just multiplying by 1. And same thing here. But you'll see that now they'll have the same denominator. They both have an x plus 7 and an x minus 3. And so that's good. And then we'll be able to add them, right? And so we're going to keep the denominator the same, because we don't have to multiply that out because we're not going to change it. But we do need to multiply the top out. So we take the 4 and we multiply it through the numerator to get 4x plus 28. And same thing on the right. We multiply the x through the numerator. So we'll get x squared minus 3x. And now we have the same denominator. We've got the same denominator, and so that means we can combine the fractions. Let me pause for just a moment here, because from here on out, it's just a nice fraction problem. Is that okay? Can I clarify anything? Okay, so now we're ready to do the subtraction, right? So we keep the numerator the same. We just leave it x minus 3, x plus 7. And we're going to do the subtraction. I'm just going to combine them first. We've got the 4x plus 28. And then we've got minus x squared minus 3x. And I wanted to write it like this first, to point out that this negative sign, this initial negative sign that I'm pointing at right now, applies to both those things in the numerator. So it's going to make this x squared negative, but it's going to make the minus 3x positive. And you can see that here, right? Because now we can distribute this minus sign. We can take this minus sign and send it through this this parenthesis, and we'll switch both the signs. It'll become a minus x squared plus 3x. Right, and so we'll get 4x plus 28 minus x squared plus 3x. And then we can finish it off by just simplifying things, right? Because we can do the 4x plus 3x to get 7x. And then we're done. So we got a minus x squared, we got plus 7x plus 28, all over our common denominator x minus 3x plus 7. Questions about that? Yeah.
Would it be wrong if you just like sum the denominator?
If you multiply the denominator out? Nope, you could definitely multiply the denominator out. It's just extra work that we don't necessarily need to do. Like here, we needed to multiply these together because we wanted to eventually subtract the top and the top. But the bottom just stays the same the entire time, right? We don't actually do anything with it, so you don't have to. But yeah, if you wanted to multiply it out, that would be just as good, yeah. Just be careful for two. Like there's the other reason I would recommend not doing that is because it's an unneeded step that you might make a simple error with, and then if you try to answer it, you wouldn't know whether or not you made an error multiplying that out, or maybe multiplying the top out, or the subtraction. So it's just another unneeded step that could be a potential problem. But absolutely, you can. Other questions? Yeah.
How did negative 3x turn to positive 3x?
Yeah, so when we did from here to here, they had the same denominator, right? And so that means we can do the subtraction. And so this negative sign applies to both of those things. And so when I combine them together here, all I did was I took the numerator of both of them and combined them. And so this negative sign multiplied through here, it made this negative and it made this one positive. So that's where that one came from. Yeah, so we had this distributed through there and made it positive.
Would you group the 4x and the 28 and the x squared and then the 3 and factor out the bottom? I mean, cross multiply.
At which step are you talking about? This step?
Yeah, no, the middle one.
This one.
Sorry, I can't read this. Yeah, actually you get 4x plus 7 x minus 3.
Oh, I see what you're saying. Factor a 7 out of here.
Yeah. Or 4 out of it.
4 out of there, I mean, yeah. So you get x plus 7. So let's just think about that for 1 second. What if we factor out a minus x? Huh, that's interesting. I don't think that's going to work, but let's try it. So it was 4x plus 28 minus x squared plus 3x. See that right? And then we've got x minus 3 over x plus 7. This is an interesting idea. Let's try. So what we're talking about is just grouping and factoring, like we did last time. Grouping those two things together and then factoring them. And so, I'm sorry, can you remind me your name one more time? You already told me this name. Brian. But Brian said at the beginning is, we can pull a 4 out of that first one and it becomes x plus 7. And that's good because there's an x plus 7 on the bottom, is what he's thinking there. And then we can pull out an x. Let's pull out a minus x. And then it'll become x minus 3. And so that looks good because we've got an x plus 7 and an x plus 7 and an x minus 3 and an x minus 3. And so the question is, can we cancel the x plus 7s and the x minus 3s? We can't. I kind of felt like, ooh, maybe this is going to work, but we can't. But why? Say more. Because of subtraction, yeah. Say more. You're right, but say more. Yeah, say it. You're right.
You have like the AC over BC equal AB, so you can do like A plus B over B plus C.
Yeah, so it's this minus sign that's making it so that we can't cancel things out. Because we have, I know I said addition between them, but subtraction is a form of addition. Like if we did 8 minus 4, that's the same thing as 8 plus minus 4. And so you can think about subtraction as an addition problem. And so we have that subtraction in there, which is making it so that we can't cancel those things out. That was a good idea, and when you first said it, I was like, yeah, that might work, we'll see. But that minus sign's stopping us. You see what we're saying?
Yeah, I didn't get that far because I started copying things.
Okay, yeah. Yeah, but that was a good thought. That was definitely a good thought and worth pursuing. Are there other questions about that? Is that okay? Great. I'm just going to try this one too, since this one is not as straightforward as the last one. So the first thing that I wrote down at the top, if you look at the top of the page here, is you usually want to factor. Where did I look at that? I thought I wrote that down here. Maybe I didn't write it. So let's write it down here. If the numerator and the denominator can be factored, you should do that, because that helps you figure out what the common denominator is. And so, I thought I wrote that down. Let me just double check. Oh, I did write that down. Right, the easiest way to find a common multiple is to factor each denominator and then take the product of the distinct factors, right? And so in this first one, we didn't have to factor anything because there was nothing to factor. But in the next one, we can factor both of those. And you know, because as it's written right now, it's really not clear what the common denominator is. But if we factor both of them, let me just cross that out. If we factor them, we can get that. And so this is actually almost that exact same problem you were talking about before, Anna, which is this can now factor into t minus 2, t plus 2, that first denominator. And the next denominator is actually an answer to a homework problem this week. T minus 2 squared can be factored into, or can be rewritten as maybe, t minus 2, t minus 2. Right? That squared just means you multiply it by itself. And so that's what I did. And again, the reason we want to do that is because now it's very easy, or it's easier at least, to see what the common factor is, the common denominator, I mean. And so when I'm looking at this, I'm seeing that this one has a t minus 2 and a t plus 2. So we're going to need at least those two. So our common denominator we're going to need the t minus 2 and the t plus 2 because the left one has those. And then on the right, the one on the right has 2 t minus 2's. And so we actually need a second t minus 2. And you can see, if you look up at the notes, the instructions at the top of the page, what I wrote was, once you've determined the common multiple, you just multiply together all the non-repeated factors. And so I'm taking all the distinct factors and I'm just writing them down right here. And if both of those fractions have that denominator, we'll be able to add them together. So I need to give the one on the left another t minus 2, and I need to give the one on the right a t plus 2. And then they'll all have the same. Any questions about that? So the way we do that is by multiplying by different forms of 1, right? So we'll get, we'll rewrite the left-hand equation here. We need to give the left-hand equation a t minus 2 because the one on the right has 2 of them. So we'll multiply by t minus 2 over t minus 2. And now you can see the one on the left will have that denominator that we're looking for. So that's good. And then we'll do a similar thing with the one on the right, except the one on the right needs a t plus 2. And so we'll multiply by t plus 2 over t plus 2. And that's good because now it has the right denominator. Now they both have a common denominator. They no longer have a 1 in the numerator. They're going to have something else, but that's okay. But now we can combine them. Just pause there for 1 second. See if you have any questions. So I'm just going to rewrite it in its ready to go form here. We'll get t minus 2 over t minus 2, t plus 2, t minus 2, plus t squared plus 2t over that same denominator. And now they've got the same denominator. Whoops, I forgot my parenthesis there. Now they have the same denominator, and we can add them. We can just add straight across the top. You keep the denominators the same, you add across the top. And I won't say that. Any questions? And so when we add them, we can, we'll do the t plus 2t, right? T plus 2t. And that'll be it, right? There's no constants and there's no t squared, so we'll just do the t plus 2t will give us a 3t on the top. And everything else is the same. Those are the only two like terms. Questions? And so I just want to point out that this is very much like adding normal fractions. I know I've said that before, but it's the same thing as adding normal fractions. So if you struggled on the quiz the other day because you had a hard time adding, the 1/3 plus the 1/4, I hope this helps a little bit because you do the same thing with those two. You need to multiply the common denominators together, and then you can add the fraction. Just ask one more time if anyone has any questions about that. Great. We're making moves today. Got to push through this review and then we can get into some more interesting stuff here. Yeah, okay. Ooh, compound fractions. That's good. That's interesting stuff. Everyone's all set with that page? No one's writing? All right, compound fractions. Love them. Love to hate them. So compound fraction, let's read what it is. A compound fraction is a fraction where both the numerator and the denominator, or both sometimes, are themselves fractional expressions. And so, in other words, it's kind of like you have a fraction inside of a fraction. And you can see that's what we have on this, like this very first example. We've got a fraction. Right, here's the numerator. This is the numerator, what the purple pen's pointing to. And then the denominator is another fraction. And each one of those have a fraction inside them themselves, right? And so that can be problematic to say the least. And so we want to learn how to get rid of that situation. We want to, if we have something like that, we want to make it not that, right? We want to make it just a normal fraction. Normal fractions are hard enough. We don't need a compound fraction. And so there's two methods to do that. We'll talk about two ways to do it. You can either A, combine the numerator and the denominator and then invert the fraction. So that's what we just learned on the last page. Like if we wanted to add x plus 1 over x plus 2, we know how to do that now. Or B, multiply the numerator and the denominator by a common factor. What I mean by common factor is common denominator. And that'll get rid of the fraction as well. The compound fraction. I recommend B. I like using B. I think it's the easier / faster method. It's definitely faster. You can decide whether it's easier. You're welcome to use whichever one appeals to you. And so I'd like to do one both ways here. Yeah, let me do this one both ways. We should have enough time for this, and then we'll end on this here. So what I want to do in this, so you can see we're going to talk about this fraction. I've got two methods. I'm going to do it method A and method B, and then you can decide which one you like. Okay, so method A is to just combine the numerator and the denominator. So do the addition and the subtraction, and then just invert the fraction. Okay. Actually, let me just see if I should reference something on the last page here. that down. I'll just leave it for now. Okay, so method A. What's the common denominator of the numerator? Just the numerator. Ignore the bottom. So ignore most of this problem. Yeah, x plus 2 is the common denominator on the top there. And so what's the common denominator? Oh, it's the same thing on the bottom. It's also an x plus 2, right? And so the common denominator is x plus 2. Because when I rewrite this problem, it's kind of like we have x over 1, and I would leave some space there, plus 1 over x plus 2, and it's being divided by x over 1 minus, I would also leave some space there, I didn't follow my own suggestion, minus 1 over x plus 2. And so if I'm going to combine the numerator and combine the denominator, the common denominator is x plus 2. So if I can give this an x plus 2 and this an x plus 2, we'll be all set. And so I'm going to multiply by x plus 2 over x plus 2, because that's going to give me that common denominator. And then we'll be able to add them or subtract them. As you can see, now when we do this, when we multiply that out, we'll have an x plus 2 in both pieces. All right? And so this is going to equal x squared plus 2x over x plus 2 plus 1 over x plus 2. And then x squared plus 2x over x plus 2 minus 1 over x plus 2. So let me let you think about that for just a second there. So I was trying to find a common denominator so that I could combine the numerator and the denominator, and I realized that my common denominator is x plus 2, and so I'm making sure that both pieces have that. And so that's all I've done so far. These problems look like super confusing because they're compound fractions, but like, just try to look at each piece and let me know if you have any questions about it. Does that seem okay so far? Because now we can add them, right? We can just do like x squared plus 2x plus 1 over x plus 2. So I just added the numerator together. I kept the denominator and added the top. And I'll do the same on the bottom, except I'm going to subtract. And now I'm in a situation that's helpful. Because what I can do now is, this is a division problem. I have a fraction divided by another fraction. And we just said that when you divide fractions, you flip the one doing the dividing and multiply it. So what we're going to do is we're going to take this and we're going to flip it and multiply by the top. And then it won't be a compound fraction anymore when we do that. So I'm just going to make a line here. We're not going to go past this. When we flip and multiply, we get the following. I flip the bottom. Whoops, that should be x plus 2. X squared plus 2x minus 1. I flipped the bottom, and I'm multiplying it by the top now. And then we can cancel the x plus 2's, because they have the same thing, right? We've got the x plus 2's here. They're being multiplied, so we can cancel. And so we'll just cancel out that x plus 2 and that x plus 2. And we get our final answer, x squared plus 2x plus 1 over x squared plus 2x minus 1. And so again, like, that approach is to combine the numerator into one thing, combine the denominator into one thing, and then get rid of it by flipping and multiplying. And so that's method A. Let me just pause for just a moment here, and you can tell me if you have any questions. Just This looks really confusing when you look at it, but I'm hoping you're able to follow along. Not too sleepy this morning. You're able to think about that a little bit. And all right, any questions about that? Does everyone see what we did? Even if it's not completely clear at this point, you kind of see the idea. And if not, you're welcome to say something. Okay, that's all right. So it's long. It also took, 1, 2, 3, 4, 5 steps or so. So I like method B because it's quicker and it gets you there quicker. That's the short of it, I guess. We might need a little more space than what I wrote down. Let me just go like this. All right. So the common denominator is the same. So method B. Let me remind you. Method B. You multiply the numerator and the denominator by the common factor. And the nice thing about that is it just cancels out all the fractions. And so the common denominator is the same. It's still x plus 2. And so what we do is we take our original problem. I'm just going to rewrite the original here. And we multiply the numerator by x plus 2 and the denominator by x plus 2, because that's our common denominator, right? And when we do that, this x plus 2 is going to shoot through and cancel that denominator, and then it's going to shoot through and distribute with that x. And the same thing's going to happen on the bottom. And so I'm going to write it out in 2 steps here. But what happens is the x plus 2 multiplies the x and the 1 over x plus 2. And the same thing happens in the denominator. It just hits every single piece, and since x plus 2 is the common denominator, it cancels out the fractions. Because you'll see what we'll do in just a second here is we're going to cancel out this x plus those x plus 2's, and we're going to cancel out those x plus 2's. And so it's not going to be a fraction anymore. It's not going to be a compound fraction, excuse me. It's still going to be a fraction. It's just not going to be a compound fraction. Does everyone see what we did there? Just going to wait until you finish writing, and then I'm just going to summarize it one more time since we've got a minute here. So we started with the original, and then what I did was I multiplied it, the numerator and the denominator, by the common denominator, x plus 2. The x plus 2 went in and is multiplying both those terms right here, and then it's multiplying both those terms right here. And you can see that since we're multiplying, this x plus 2 cancels with that, and this x plus 2 cancels with that. And we no longer have a compound fraction, right? We just have x squared. I'm going to multiply this out too, right? I'm going to send this x through here, and I'm going to send this x through here. So we got to do the distribution, but then we'll get the same answer. We'll get x squared plus 2x plus 1 over x squared plus 2x minus 1. And you can see that these two things are the same. But the second method was much shorter, right? It was just one line. And quite frankly, you could probably, once you do these enough, you can usually just skip over this middle step. You kind of just realize you do this, and you can almost just go right to here. And so it's quicker. I personally find it easier. I feel like there's fewer steps, so you're less likely to kind of mess things up. But I don't know. You're welcome to choose either one. So, any questions about that one? All right, great. I think we'll stop here today. We'll pick up with the other one on Wednesday, and we'll have that short quiz on Wednesday as well. Remember that. Okay, have a great day. So we were talking about compound fractions, and to remind you, a compound fraction is when we have a fraction inside of a fraction, right? Like what's being shown here. And we had talked about two different ways to simplify them. You can either combine the numerator and combine the denominator, and then you end up with something like this. And then you can flip the bottom one and multiply it using the division property of fractions. Or you can just multiply through by the common denominator of x plus 2. And I mentioned to you, I recommend doing that method. If you prefer the other one, that's fine, but I usually just stick with that one, and that's what I'm going to stick with on this the second example here. And so the second example is a little more complicated, and some of the homework look a little bit more like this one. This is actually very, very similar to one of the homework problems. And so what we want to do is we want to look at the denominators, right? The p and the t in the numerator, and we got the t squared and the p squared in the denominator there. We want to look at those two and think, what is the common denominator that we can multiply by that will cancel everything? Right? So there's kind of like two ways to think about that. You either think, what's the common denominator? Or the alternative sort of comparable way to think about that is, what do I need to multiply everything, what do I need to multiply by so that all the denominators cancel? Right? So like, for example, yeah, if I multiply by p, it's going to cancel this one, but that's it. It won't cancel the t, it won't cancel the p squared, etc. If I multiply by p squared, that's good because it'll cancel the p and the p squared, but not the t's. So I need a t in there as well. And so maybe if I multiply by p squared times t squared, everything in there would be canceled, right? It would cancel out all the squareds and all the single non-squared terms as well. Right? And so that's the first thing I'm thinking when I'm looking at this. I'm thinking, what's the common denominator? And it looks to me like it's t squared, p squared. Right? And again, the way we had talked about that last time is we kind of just multiply together all the distinct roots. And so when I'm looking at this problem, it's kind of like t times p times p. And I think about it that way, and I look at the equation, that's sort of proving to me that everything's going to get canceled out when I multiply by that. And so that's what we want to do. We want to start by multiplying this thing by t squared, p squared over t squared, p squared. Any questions about why that's a common denominator or what we're doing? Yeah. Because t and p, so the question is why wouldn't it just be t and p? That would cancel out the ones on the top, but it would only cancel out one of each of those, and we'd still have a compound fraction in the denominator. Right? So we need to have the squareds so that we make sure we cancel out those two in the bottom. Does that make sense? And we'll have extra ones up here. You'll see that we're going to have an extra term in the numerator, but all the fractions will be gone, which is really what we want to do. Is there another question in the back? I don't know if it was Matt or Disa maybe. One of you guys have a question?
Yeah, I have the same question. Is it just because the top one is, like, the denominator is p minus t, and the bottom one is t plus p, so it's like a negative t?
No, we don't care about the plus and the minus between them. That's not coming into play. We just want to make sure that when we multiply through, all the denominators get canceled. And so we need to have the highest powers in there to make sure that the bottoms cancel. So what were you thinking it was going to be? Did you have a thought?
It's just going to multiply the top fraction, like t over p times t, and then the other side by p, so the common denominator will still be t squared, p squared.
I see what you're saying. So you can't go in and multiply each one of these individual terms by something because you're going to be changing the problem. The key to this is that we start by multiplying it out front. So this, what I wrote down here in blue, this t squared, p squared divided by itself, that equals 1. And so we're taking our original problem and we're multiplying it by 1, which means nothing's changing. And so, but if we went in there, we multiplied that first term by something, and then the second term by something different, that's changing the problem because we're not multiplying by 1 when we do that. We need to make sure we're multiplying by 1 so that it's an equivalent problem. That's kind of an important part of it. Does that clarify that for you? Are there other questions about that? Because what's going to happen now the reason I write this out front and not just go right into the fraction and start writing it is to show you we're multiplying by 1. And then what happens is we use the property of fractions, right? So we've got these things are in parentheses, and these are also in parentheses. So when we go and do the next step, the t squared p squared is going to multiply by both of the things in the numerator and in the denominator, and everything will get canceled. But we started with just a form of 1, which makes it okay. Right, so I'll write out the details in the next step. The next step is everything is going to get multiplied by t squared p squared. Right, so there's one in the homework that's very similar to this one, except it's with y's, y's and x's. Oops, forgot to write in the t squared p squared there. And so, like Disa was kind of pointing out, everything gets multiplied by that. So this is kind of the form that she was talking about before, but everything gets multiplied by the same thing, which was what makes it okay. Right? Just like in an equation, what you do to one side, you have to do to the other side, right? That's like a cardinal rule. Everyone knows that. We have to do the same thing here. Right? We can't just pick and choose what we multiply things by. We have to multiply everything by the same thing, which means that nothing's changing. And so at this point, hopefully you can see that everything's going to cancel, right? So first of all, in the denominator, all the squareds cancel, right? So the t squareds will cancel, but we still have a p squared. And then the p squares cancel, and we still have a t squared. But in the numerator, we're going to be left with a bunch of stuff. So the denominators cancel, so like this p cancels on the numerator, but it only cancels with one of the p's. So we'll still have a p left over in this one, right? We'll have a t squared p. And then similarly with the t cancels with one of those t's. And so our final answer is going to be, we'll have t cubed p minus p cubed t. And in the bottom, we'll have p squared plus t squared left over. So let me just pause for a moment here and let you think about that one. And let me know if you have a question about it. Thoughts on that one? Questions? Comments? Clarifications? So I'll just reiterate one more time why it needs to be t squared p squared. Because that's going to ensure that everything gets canceled, right? Everything got all the denominators, all the denominators ended up canceling in this. And we were left over with some things in each situation, right? Nothing, it's not like everything canceled, right? We're left with a t squared in this one and a p. We're left with a p squared, right? We're left with a p squared, left with a t squared. There's something left over every time because we're putting enough in there to make sure everything cancels. And then when whatever is left, we just write down here. And the whole point of this, to remind you, is that we started with a compound fraction and now we don't have a compound fraction. And so that's nice. It's nicer than dealing with a compound fraction. Questions about that one? All right. Let's look at that application problem really quickly then. That one I passed out at the beginning of class here. So it looks like this. And I'll go ahead and read it. It's long. I know it looks long and it looks complicated, but I'm just trying to show you where a compound fraction might come from. Like, why would we ever see a compound fraction in the real world? Here's an example of one. So let's suppose that in 1 week, in week 1, let's say, we've got two people, Carlos and Janine. In week 1, Carlos spent T amount of time on the internet, a third of which he spent on Facebook. And then the next week, he spent 8 more hours on the internet, a fifth of which he spent on Facebook. Okay. And then let's talk about Janine. So Janine spent twice as much time as Carlos did on the internet, a third of which she spent on Facebook. And then the next week, she spent 5 hours less than Carlos did in that first week, a quarter of which she spent on Facebook. And so you don't need to know any of that stuff. The point is, we've got some situations where there's ratios. And if we took the ratio of the time that the two of those people spend on Facebook, it would be given by this equation right here. So the numerator here is amount of time Carlos is on Facebook. And then the bottom is the amount of time that Janine is on Facebook. And so if we wanted to learn something about the ratio between the two of them, like who spends more time on Facebook, for example, or something like that, this would be the equation that would help us tell us that. And we're going to carry this through into the next section, actually. So that's another reason why I like this one. But as it's written, it's nasty because it's a compound fraction. And so we can't really understand it as it's written. We can't really manipulate it very well. And so what we want to do is make it not a compound fraction, right? And so what I wrote here is simplify the expression into a normal rational expression, i.e. not a compound fraction. So let's start with our normal, the original piece. And we're going to, the other thing that's different about this is that the denominators are numbers instead of variables, right? All the examples we saw had the denominators being variables. And now it's a number. So it's a little bit different as well, and I like that too. So how do we do this one? We want to multiply through by a common denominator. So what's the common denominator of 3, 4, and 5? It's actually a little bit tricky to think about. So I would recommend thinking about multiples of 5 and then thinking whether or not 3 and 4 go into them. And so 5, no. 10, no. 15, no. 20, 4 goes into 20, but 3 doesn't. 25, no. 30, 3 goes into 30, but 4 doesn't. Okay, 35, no. 40, 4 goes in, not 3. 45, what is it? 60 is the common denominator between all those. And so the common denominator, I'll just write it here. The common denominator of 3, 4, and 5 is 60. And so we want to multiply this through by 60 over 60. And so that 60 is going to go through here, and it's going to hit that first one, and then the second, and then the same thing in the denominator. And all these numbers go into 60. 3 goes into 60, 4 goes into 60, 5 goes into 60, and so it'll cancel out all the denominators. All right, take a minute and finish that one up. So get that down to not a compound fraction. And I'd like to ask you to try that and check with someone next to you, please. All right, let's take just a minute to do that, let's say. So I'm just going to start writing it out just in case you're a little lost, but please give it a try yourself. I thought it was kind of surprising that the least common denominator or multiple of 3, 4, and 5 is such a big number. Right? I thought it would have been smaller. Chris here? Yes, Lee. Alright, now's the time where you finish up and then you say, hey, did you get this? And they either say, yeah, or, huh? And then you talk about that. And if you're lost, that's okay. Remember, it's okay to tell the person, I'm a little lost here. I'm not sure if this is right. I'm not sure what I'm doing. I didn't know how to start. Okay, I'm trying to be patient here, but I'm just going to go ahead and just say it. Can you please just turn to the person next to you and talk to them? See what they did, and please just start doing it. I know it's early. I didn't sign you up for this class. Please, I'm begging you. I've begged you now. Is that helping? I don't know. Okay, thank you. I'm going to start doing this one now. So the whole point of multiplying, are there questions about this first step? So we multiply by 60 over 60. It goes through and hits all the terms. And so that's what I wrote down here. The 60 is multiplied by all the terms. Is that part okay? And so the point of doing that is because like 3 goes into 60, 5 goes into 60, 3 goes into 60 again, and 4 goes in. So everything goes into 60, so we can rewrite this as, right, 3 goes into 60 20 times. That'll be 20t. 5 goes into 60 12 times, so we'll have plus 12 times t plus 8. Again, 3 goes into 60 20 times, so we'll have 20 times 2t, which is 40t. And then that should be in parentheses there. 4 goes into 60, what? 15 times? Yeah, thanks. So this would be plus 15t minus 5. And now we don't have a compound fraction anymore. Like, yeah, we could multiply the 12 through there, and that'll be helpful too. But I'm just going to leave it like that for right now because it's not a compound fraction. The point of this problem was to make it not a compound fraction. So we no longer have a compound fraction. And we're going to come back to this problem in a second, or not in a second, but in the next section, I meant, when we're solving equations, we'll go ahead and we'll solve this equation equal to something. So keep this one in mind for next time, yeah.
Why wouldn't you distribute the 60 to the, like, denominators as well? So do like, t times 60, 3 times 60, plus 60 times t plus 8, and then 60 times 5.
So when we wrote this down the first time, this top 60 goes into the numerator and the bottom 60 is going into the denominator. Is that part okay? So only one 60 is going into the numerator and a single 60 is going into the denominator. And so then when we have something like this, when we have this t over 3 times 60, it's like a 60 over 1. And so when we multiply fractions, we multiply straight across. And so we get 60 times t over 3 times 1. Right? The 60 would multiply into the denominator if there was a 60 down here instead of a 1. Right? So in this situation, that looks like this. And so the 60 doesn't go into the denominator because it's the 1 goes into the denominator. The denominator.
So how do you get 20?
Because I divided 3 into 60. Right, so these two, this gave us that 20, this gave us that 20, this gave us the 12, and then this one gave us the 15. 4 into 60. This one?
Not like it's t over 3 times 60. So what happens to the numerator?
So t over 3 times 60, I'm doing that right here, right? It becomes 60t over 3. And then 3 goes into 60 20 times. And that's where this 20 came from. Right, this 60 multiplied the t over 3, and so I'm showing you the work of that down here. You multiply straight across the fraction to get this, and then 3 goes into 60 20 times. And it's similar for all these, right? So 5 goes into 60 12 times. That's where that 12 came from. 3 goes into 60, that 20 times. But then you multiply it by 2. So that's why this is a 40. And then this one came from 4 going into 60. It's 15. Other questions?
Where you put the, in the denominator, you put from 3 to 60 is 20 and decimals.
3 goes into 60 20 times, yes. And then we multiply it by that 2, which gave us 40.
Oh, okay.